Na sequência, nós vamos ter mais uma palestra convidada, a palestra internacional. E a transmissão tá ok? Pronto? Então, queremos começar agradecendo mais uma vez os patrocinadores do SBBD. Temos hoje à tarde um recado importante, que hoje à tarde o tutorial ele começa às 13 horas, tá? Então tem uma mudança no programa aqui. Aliás, não tem uma mudança, é uma diferença no programa. Já estava programado para começar às 13, só lembrando disso. Tá? Então agradecemos mais uma vez os nossos patrocinadores, a CockroachDB, Cockroach Labs, a Stone, temos a Solids, temos a Google e a Alfa Engenharia. Agradecemos todos os nossos patrocinadores, também as agências de fomento, CAPES e FAPEMIG. E um recado das mulheres: a foto tradicional das mulheres será hoje à tarde no coffee break ali em cima, certo? Então a foto será ali em cima das mulheres, ok? Então todas lá. Agora eu convido a professora Carmen. Então agora eu convido a professora Carmen aqui para fazer a apresentação do nosso keynote.
Welcome everybody. It's a pleasure for me to introduce a dear friend and a colleague from my PhD long time ago, but Alin Deutsch, and I'm going to read his bio. Alin Deutsch is a full professor of computer science and engineering at UC San Diego, where he also serves as faculty director of the Masters of Advanced Study program in Data Science Engineering. His research interests include query language design and optimization for various data models, ranging from text to the relational and post-relational models, with particular emphasis on graph data that he's going to talk today. He has also worked on cross-model data integration and an automatic verification of business processes. He earned his PhD in computer science from the University of Pennsylvania and MSc degree from the Technical University of Darmstadt, Germany, and BSc degree from the Polytechnic University of Bucharest, Romania. He is the recipient of the 2019 ICDT Test of Time Award, the 2018 Alberto Mendelssohn ACM Pods Test of Time Award, the ACM SIGMOD 2006 Top 3 Best Paper Award, a Jean D'Alembert Excellence Fellowship from the University of Paris-Saclay, the Alfred P. Sloan Fellowship, and an SF Career Award. So thank you very much, Alin, for coming and giving us a talk. So the floor is yours.
Thank you, everyone. It's a great honor to be here. Thank you for the invitation. It's also a great pleasure. Turns out to be a nostalgic trip for me because, as you've seen, I have very good old friends here, Sergio included, and I'm happy to make new ones. But as I was preparing this talk, there was even more nostalgia because I found myself going back to when I was starting undergraduate, who got excited by this hot topic in databases that made me want to do research in databases, and I ended up doing a doctoral research in that very topic, and that topic was graph databases. So, I was thinking, started to question myself when somebody in midlife starts looking at the research of their youth, maybe it's just a sneak onset of midlife crisis, and it's not really objective. So the purpose of the rest of this talk is to convince you that no, this is not due to midlife crisis, and that actually there is a good reason for revisiting this research. And moreover, if it is midlife crisis, then I've always had it. And the reason is that graph database research has been around for, well, I remember 30 years of it. And it never really went away. It just kept changing its shape. So we started with what we at the time in the 90s we were calling semi-structured data. And that was the first instance of excitement about unrestricted graphs, which at the time were simply motivated by modeling the World Wide Web. The nodes of the graph were the pages, the links between pages were modeled as binary edges, and we were typically interested in answering reachability queries between these nodes. Then, while there wasn't much industrial uptake of that way of thinking and the research that came out of it, there was a lot of excitement about the next generation of graph databases, one in which the graph shape was restricted to hierarchical, tree-shaped graphs. And that was, of course, XML. And as you know, that one led to much more industrial uptake. There was an entire ecosystem of standards that were developed under the umbrella of the World Wide Web Consortium, XQuery, XPath, and so on. And then, of course, the database community being so fickle and fashion obsessed as we are, we moved on from this one and we went to something that was rather isomorphic, document databases, JSON, which if you look at it squinting, this is also just tree data. And a lot of the ideas that had been developed for XML, XML querying, optimization, do actually apply in the JSON arena. And some of the important systems there, of course, there's MongoDB, but there are a bunch of others. Some of them have led through multiple steps to SQL++, an extension of the SQL standard, which has been implemented commercially in Particle, Amazon Redshifts query language, and that was driven by my colleague at UCSD, Yannis Papakonstantinou. But interestingly, in about a decade ago, we went back full circle and started looking again at unrestricted graphs, no matter what their shape, cycle included. And this was initially motivated by analytical tasks over social networks where the users were the nodes and the following relationship, friendship relationship between them was the edge. And of course, here there would be cycles, there would be cliques of users. So all of a sudden, you need to look at the unrestricted scenario. And in the meantime, of course, the paradigm has been widely adopted. After all interesting data is linked. Okay, so we're back where we started. So you might ask, okay, let's first get to a common denominator here. When I talk about graph data models, I mean nodes and edges which carry their own additional data. So the nodes will model the entities of the discourse. The edges will model binary relationships between them. Edges may be directed or undirected to model asymmetric, respectively symmetric relationships. Asymmetric, I follow you on Twitter. Symmetric, we are siblings. Nodes and edges may have types or labels, and each of them can carry data. Think of them as sets of key value pairs, okay? Called attributes in the literature. More recently, these are called properties. Here would be a little example. Let's say that we have two types of vertices: products, which have a name, a category, a price; customers, which have social security number, name, address; and an edge type we call bought, which carries with it the discount at which something was bought and the quantity in which it was bought. So the fact that customer C bought 100 units of product P at discount 5% would be modeled by an edge going from the node that models customer C to the node that models product P, and carrying the data. Since this is graph data, it's easily depicted. The blobs here would be the nodes, the arrow is the edge, and these rectangular callouts would be the attributes, the properties that we attach to both vertices and edges. Of course, one typically has more than one sale. So if I put all the sales together between all the customers and all the products in my database, I will get a graph like this. And notice that nodes might have multiple edges, like this product in the middle here. Sorry. Forgot how to open this. Ah, I did. Thank you. It should work now. Okay. The node in the middle here is bought by two customers. This customer buys two products, and so on. Okay, so why revisit the field from a research point of view? Well, first of all, as opposed to Graph 1.0, back when I was getting excited about this, that was a simple academic exercise. There were only academic research prototypes. There were no commercial products. That has changed dramatically. In the meantime, the industry is clamoring for graph databases. There is wide interest to the point where graph query languages are being standardized. As a matter of fact, the standardization has been going on since 2016, and the first versions of the standards are coming out this coming year, 2024, in the beginning. One of them is called SQL PGQ, and it is an extension of the SQL standard. So there will be an additional chapter to the official ISO ANSI SQL standard dedicated to graph pattern matching, their semantics, and so on, how they can be manipulated by the rest of the SQL around it. And then there is a second standard which shares the pattern matching syntax and semantics with SQL PGQ. It's called GQL, the Graph Query Language Standard. It is also ISO ANSI. It's actually the very first query language since SQL, so in about 40 years, that is picked up by ANSI. And this one talks about native graphs. They don't have to live together with the data in the SQL database. It's standalone. So it has much more to offer, including how you define the schema of a graph, and so on. Then there exists an organization known as the Linked Data Benchmarking Council, LDBC, made up of both industrial and academic researchers. I happen to be a member of it, which is now standardizing benchmarks for graph engines. This is how widespread these artifacts are. And we're also talking about pretty large scale factors at which these competing engines are working. The benchmark has currently been run by various vendors at 10 terabytes, at 30 terabytes. They're working on at 100 terabytes. So this is far from the toys that we had in the 90s. Okay, now this is the impact. What about research? Is there anything new that is worth researching about this new trend? I escaped. Well, if you listen to the industrial technical writers and to the various evangelists in the industry, they make a lot of marketing claims, some of which are exaggerated. However, there is an important seed of truth at their core. So here, for example, the statement is that graph technology is a revolutionary break from the relational world. It allows you to solve problems that relational technology cannot. You think differently, you implement differently. Okay, maybe this should be taken with a grain of salt. Let's look at some of the more specific claims that are being made. One of them is that it's more natural to think about the data, to conceptualize it, than in the relational model. Well, okay, here is where I usually end up telling them, remember the ER diagrams, the way we actually always wanted to do relational databases to begin with, the way we teach our students to organize their data logically, which they promptly skip over and they go directly to the tables. But in their mind, even if they don't realize it, this is how they think. And I would claim that we always wanted to think about data as graphs and linked. It's just that the technology that arrived didn't quite support it because it forced us to think tables and it forced us to join tables and so on. But from the conceptual point of view, this is nothing new. We've had ER diagrams. Okay, if you look at tables, then yeah, I agree that it was much more natural to draw the edges between the entities rather than try to make my way here through, okay, there is a 1 here, where do I find the 1 in the other table, and so on. Okay, so I will give to this hype a partially true fact check. If you're talking about naturality of manipulating data as tables, yes, this is not as user-friendly as graphs, but if you think more broadly ER diagrams, then it's really nothing new. Here is another claim that is being made very frequently, which has to do with performance. So the claim is graph traversal is more efficient than computing relational structural joins. Because in native graph storage, the edges really correspond to pre-computing these structural joins. So instead of at runtime finding which tuple from here matches which tuple from there, I have it pre-computed, I just read it from my storage. And this is actually one argument that I tend to buy. Except, yeah, of course, imagine doing this over the tables. This is going to take some computation. But let's not forget that recently we have seen tremendous improvements in relational join technology. We have seen the advent of column stores and the joins related to them, worst case optimal join algorithms, the join supporting indexing schemes. And as a matter of fact, there are, even in this graph database setting, a bunch of commercial and academic prototypes that use exactly these techniques coming from the relational world for graph querying. I would like to just quickly point to two of them. Relational AI, which is really the best relational join engine out there, developed for a much more general problem, computing recursive tasks over relational tables, using data log extended with aggregations and a bunch of bells and whistles. It incorporates all the best techniques from worst case optimal joins. As a matter of fact, among the important figures You have Hang No and Mahmoud Abu Abbas, who are among the parents of worst-case optimal join algorithms. They work with Dan Suciu and Leonid Lipkin and Dan Olteanu, which are all other highly visible database researchers. They have a bunch of best POTS paper awards under their belt on this very topic. So there is a lot of promise in this approach to querying graphs. The recursive data log allows you to write reachability queries, exactly what you need in a graph scenario. And then let me mention an academic prototype coming out of University of Waterloo. This is a graph-specific engine, but it incorporates all the goodies, column storage and worst-case optimal joins, and specialized indexing techniques in order to answer graph queries. Still, one might say, even if they do it in the best and smartest way possible, they still have to spend computation effort at runtime as opposed to just reading the edge. So which school of thought will win here is really not clear. The jury is still out, but if the relational approach will make an impact, keep an eye out for relational AI. All right, here's another claim that is being made. Yeah, sure, semi-structured database existed 30 years ago, but in the meantime, we have much more modern computation frameworks, massively parallel computing, the cloud. As I was saying, the LDBC benchmark at this point is requiring scales of tens of terabytes, so we are talking pretty large graphs here. And this requires revisiting the research foundations, something that I fully agree with. And this is really the reason why it makes sense for us to have this kind of conversation. Now, as soon as you revisit the foundations, you find yourself in the exact same debate that we had in the 90s. How do you build a graph database? Do you put it on top of relational backends? Or do you build something native from scratch? And both approaches had nice successes to show in the 90s. None of them really emerged as the winner, and the debate was for a while forgotten as we moved on. But now we're back. And as I just mentioned for the two systems on the previous slide, column storage, worst case optimal join, and so on, they have been developed for relational technology, and they come to bear in graph querying. But there are also novel graph-specific native infrastructures that have been developed, and this is what I would like to focus on today. Okay, because talking about the best techniques from relational database research, that would be a much broader topic. Now, it turns out that these novel infrastructures, they trace the lineage back to NoSQL programming style. And the adaptation for the particular case of graphs is known in some circles as think like a vertex, also vertex-centric programming. Okay, this is a computing abstraction for parallel computation. Conceptually, every vertex is a processor, and the vertices all execute in parallel from each other. Running a so-called vertex program is the same program for all vertices. And the instances of these programs running on the vertices, they communicate with each other via messages that they send to or receive from neighbors. And the vertices typically execute in lockstep via synchronization barriers. This is really a special case of the famous general programming paradigm known as bulk synchronous parallel computing, introduced by Leslie Valiant. It was first adapted for graphs specifically by the Pragal system coming out of Google. Then it was picked up by a bunch of open source systems such as Giraffe and GraphX and many others. The Pragal program executes also in lockstep as a series of super steps, and at every super step, all the vertices work in parallel logically. They receive inbound messages sent in the previous super step. They compute based on them and the value stored at the vertex a new value, and then they send messages to their neighbors, which will be received at the next super step. Here is a variation that was introduced and used, known as GAS, gather, apply, scatter, which is conceptually isomorphic with Pragal when the vertices evaluate in lockstep, but it also supports asynchronous evaluation. It was introduced by the Graph Lab system, another open source project at the time. And here, the vertex program is organized in 3 phases. In the first one, a vertex gathers information from its neighbors. It can read the attributes at the neighbors. Then, in the next phase, the apply phase, from this information and from the information stored at the vertex, a new result is computed and stored at the vertex. And then, in the scatter phase, the neighbors will receive this result and they can update their own values. Okay. Here, the difference in thinking is that the communication abstraction, rather than relying on messaging between nodes, is shared memory. A node can just read and write the attributes of its neighbors. Let's escalate a little bit more. Power Graph came along. It refines the gather, apply, scatter abstraction to process edges in parallel, not vertices. And the motivation here was that you might have some very high degree vertices that have to do so much work while the others are done, so they end up being the stragglers and slowing down the whole computation. Okay, when you have edges, you can just have the same amount of edges taken care of by each thread in your implementation. In the gather phase, a function is executed over all the edges. Then the results of these functions are reduced by a user-defined sum function. And then the apply phase uses this reduced result. And I should also mention that the only edges that are allowed to work are the ones incident on an active set of vertices. Let's extend this a little bit more and apply basically all the good ideas we've seen in something introduced by graph startup Tiger Graph, which it refers to as the edge map vertex reduce programming paradigm. It's also parallel processing. The computation starts from an active vertex set, and it can consist in maps of 2 kinds. You can either map the same function over all the vertices that are active, or the same function over all the edges that are incident on the active vertices. Okay, and at the end of this, you're going to compute the next active vertex set. As the vertices or edges are mapped over, these functions running at each of them compute some output, and that one is going to be reduced at the vertices into aggregating containers that are known as accumulators. So let's look at a bit of an example here. I have this graph. I start from an active vertex set that I show here, the blue vertices. Then I can run a vertex map, which would basically run the same function at each of these vertices. But I can also run an edge map that would run the same function on all the edges incident on this active vertex set. And at the end of the edge map, I will determine the new set of active vertices. And of course, I can now repeat. What's interesting technically here is how the results of the mapped functions are aggregated. And they are aggregated into something called an accumulator. Think of it as a container that holds some data value. It accepts inputs, and it aggregates these inputs into the data value using a binary operation that is attached to the accumulator. For example, if I'm building a big sum of all the inputs, then I just use the binary sum to take an input at a time and add it to the value inside. There are quite a few such accumulators that come built in, such as sum, max, min, etc. But they can also be user-defined. You can write whatever you like. These accumulators may be global, by which I mean that you have a single container instance for the entire query, or they can be vertex attached. You will have one copy for every vertex. And they are first-class citizens. They can be mentioned in future steps. Their values persist between steps, so the next step can compute with them just as it computes with the values of the attributes in the graph. Let me give you an example. For the task of looking at my database of customers and products they bought and computing both the revenue per customer and per product, I'm going to start by equipping the customer nodes with an accumulator that I call C sales. The @ sign there just tells you it's an accumulator. Moreover, it's a vertex attached one, so every node will have one. And for product nodes, I will equip them with P sales accumulator. And then during the edge map, the function that looks at this particular edge will compute the sales revenue from this particular sale. Of course, it would have to access attributes that are attached to the edge and to the product in this case, and it will make a single value, call it this sale revenue. But then the interesting part happens. This value will be written into both of the accumulators. This is the revenue from the same sale, but we have to keep track of it for the customer's revenue, for the per customer revenue, but also for the per product revenue. And how does this work in the entire graph? Well, all the nodes are equipped with these accumulators. We start from this vertex set, let's say, and then we operate over all the edges. This first edge computes that revenue, it sends it to the two accumulators, but there are other edges that do the same. And here you see one of the issues. This customer has bought two products. There are two edges that work in parallel, computing a revenue, and they have to add it to the customers, the same customers' total sales. And this has to be done carefully so as not to have the right of one edge override the other. And this is really implemented in a parallel, safe way as a producer-consumer paradigm in which the consumer is the accumulator itself. And as it sees inputs, it just sums them up. And the similar thing happens here where I have two edges incoming into the same product because two different customers bought it. Again, the two sales have to be summed up. All right. So this gives us a segue between the low-level programming paradigms and the high-level query languages out there. And there are many. And what I'm showing you is not necessarily the most representative, but it's the only one that allows me at the high level to program accumulators. I'm going to give you 1 or 2 examples of it, but then I'll tell you about the standard query language, which is not this, but there are many primitives that are in common. Okay, so what I have just explained to you can be expressed in this little query here. This is all of it. First of all, we have in this first line the declaration of our accumulators. And notice as type, we give them some accum of float. We're saying that the value inside is a float and the inputs it expects are floats. And moreover, it will sum them up. And then if you look at the query block, it has a select from where clause, very much inspired by SQL, but it also has this new clause, the accum clause, which tells you what the edge map function is actually doing for every edge. Okay, so the active vertex set in this case is very broadly defined as all the vertices of type customer. The from clause contains this pattern which filters which edges will even undergo the map. And this pattern is actually identical to what GQL and SQL PGQ standards are bringing out. It basically says that we have here a customer C. This is a variable binding to nodes of type customer. This variable P binds to nodes of type product, and only if there is an edge oriented from the customer to the product of this type bought, and we introduce a variable to refer to that edge B. And then in the accum clause, notice how we can access the attributes of the edge B and of the price node P in order to compute the sales revenue. We can also introduce a local variable here so that this variable, the value of this variable, is going to be written into the C sales accumulator at the node C and into the P sales accumulator at node P. Okay, so this accum clause is really the map function, the edge map function. Also notice the select clause outputs P, the product, and the set of all these output products can be captured in a vertex set named products here. This will be the new active vertex set from which we can continue doing further computation. And interestingly, notice that we have used the same sales revenue to contribute to 2 aggregations of the same data, but according to 2 distinct grouping criteria, one by customer, one by product. Okay, and if you try to write this in SQL, most people will end up writing 2 select from where blocks, because you can't really specify that you want to take the same data and group it this way or the other way in the same block. And you will need a good optimizer to realize that the 2 blocks share the select from where part. It's just different group bys clauses, and therefore it should not traverse the data twice. Okay. Now, if you know the bells and whistles of the SQL standard, you know that there are ways to specify for the same traversal of data that you want to compute multiple groupings. But they are not as fine-grained as what I'm showing you here. You end up computing more group bys than you actually need. Okay, you can say I want the set of all possible ways to group if you take all the subsets of this attribute list, for example. And the groups are distributed. This is parallelizable and distribution friendly. The result of the sales stays with each node. A customer node has its own sales revenue. A product node has its own sales revenue. There are benefits to aggregating in this accumulator-based way that transcend the graph model. This subsumes SQL aggregation. As a matter of fact, SQL's group bys were implemented in Tiger Graph asyntactic sugar using these accumulators. You can specify queries that are naturally parallelizable. And this facilitates specification of single-pass multi-aggregation queries that are only partially supported in SQL, as I said. Even the most sophisticated aggregation primitives will compute wasteful aggregation that you don't need. We ran some experiments showing pretty significant speed-ups of accumulative-based aggregation versus group-by SQL-style aggregation that we published in a Sigmund paper 3 years ago. Okay. Let me continue talking about the ramifications of the fact that in modern applications, a lot is about computing analytics, a lot is about aggregation, something that was kind of an afterthought in the semi-structured graph research in the 90s. One interesting ramification is that once you want to aggregate, you do care about duplicates. Maybe you want to count all the products that two people have bought in common. That's a typical thing you do in recommender-based systems. And if you work under set semantics, which was the go-to of the semi-structured research, then you will have baked in duplicate elimination, which in many situations is not what we want. And just like in SQL, in practice, you want to resort to back semantics. You want to keep all duplicate entries, to count correctly, to sum correctly, and so on. But as opposed to SQL, once you do that, you run into issues of both semantics and performance. So in current graph query languages, the multiplicity of a source target pair of nodes in the output of matching a pattern against a graph equals the number of distinct paths that connect the two. And the problem with this is that even in non-cyclic DAGs, this number can be exponentially large in the size of the graph. Here, the typical chain of diamonds example, in which I want to start from the node at the leftmost corner here, and I want to go here, and if there are n such diamonds chained together, I have 2 to the n possible paths. More serious, if the graphs are cyclic, then there are infinitely many distinct paths, depending on how many times I go around cycles. So it's not even well defined what the multiplicity is. For that reason, there are a bunch of solutions that have been adopted in practice, and I'll show you how they have made it into the standard. One of them is to just bound the traversal length. If you have some construct that uses the clean star, meaning do an arbitrary number of repetitions, well, there is syntax that looks like this, in which you put integers here and you say, I want at least this many repetitions and at most this many. And this will ensure that you have only a finite number of paths that are even relevant here. And this is supported by all of the reference systems out there. Here are two other solutions that are supported and used in practice, even though in worst case, they are both intractable. Restrict the kind of traversals over cycles that are considered legal. So one of them says, do not repeat vertices as you traverse. Okay, so that leads to only counting simple paths. Okay, you cannot enter a cycle because then you won't be able to exit it. This is recommended in style guides and tutorials of the Gremlin Apache project. There is a predicate that checks that the path is a simple path there. The problem is that the membership of a source target pair in the result of a query is an NP-hard decision problem. And this is not the kind of NP hardness that we have lived with all along when we were matching an SQL query against the data, because that one was NP hard expression complexity, and the size of the SQL query was nothing compared to the database. Here, we're talking about data complexity, NP hard in the size of the graph. So if things get bad, they get really bad. Another solution that has been adopted in practice by Neo4j's Cypher query language is to allow to go around cycles, but do not repeat edges. Okay, so I can go around the cycle once, second time I would repeat edges. These paths are called trails. This is the default semantics in Cypher. Turns out it doesn't really improve the computational complexity. You have the same NP hardness issue. Here's another way to think, which leads to attractable and aggregation-friendly semantics. Namely, just look at the shortest path that satisfies a given pattern. So if I have a pattern, then I'm going to say that the pair of source target vertices is in the answer of matching this pattern. If there is a path connecting them, the edges on the path, they spell a word that satisfies the pattern, as we used to have in semi-structured data cases. But the path is the shortest among all such paths. And of course, there could be ties, in which case I want all these paths. Still, there will be only finitely many of them, and I will count them. Okay. Now, the interesting thing here is that counting the number of shortest paths that satisfy a pattern can be done in polynomial time, even though there are potentially exponentially many such paths. And this is the default semantics of GSQL, the query language I have shown you some flavors of. Just to quickly contrast the match semantics flavors, if you consider this graph and the source and target vertices to the left, respectively, right? And the pattern is just E star, so an arbitrary chain of E edges, E-typed edges, must be matched. Well, then the pair ST is a result of this pattern. However, if I look at unrestricted path, then it comes up with infinite multiplicity, because I can go around this cycle here an arbitrary number of times. Every time it's a different path. So I can't really count these unrestricted paths. For the simple path, I have this one here, the horizontal, and then I can go down here and up, and then I can go down here and up a bit later. So I get 3 simple paths. In Gremlin, with a simple path predicate, I would have multiplicity 3. If it's a trail, then I can do all the simple paths you've seen plus one more that goes around this cycle, but only one, so as not to repeat edges, and then continues to T. So that gives me multiplicity 4. And then on the shortest path semantics, multiplicity is 2, because there is this straight path here containing 5 edges, and there is another one that goes down here and then up here, also 5 edges. But I cannot continue this way, because that will give me 6 edges. This is not the shortest path, and any attempt to go around the cycle here will only make the path longer than it could be. And before you think that there is a clear hierarchy between the various semantics in terms of each of them giving fewer paths, that's not quite true. Things are more complicated. These are really incomparable. Consider this other pattern that says I want to follow an A edge, from there a B edge, from there another B edge, and from there a C edge. If you look at the source target pair here, it's going to be an answer in quotes, but on the simple path semantics, it will have multiplicity 0. It's not really an answer. Okay? And there is no simple path that follows 2 B labeled edges from S to T. I would have to enter the cycle. At that point, I would have to come out through the same node. Similarly, there is no trail either, because while I can go around this self loop once, I need another B edge, and I would have to repeat the traversal of this edge. And finally, the shortest does exist. I would just go around this cycle once for the first B edge, then around it again for the second B edge, and then I continue to T. This satisfies my constraints on the shape of the pattern, and this would be the shortest, so it would come out with multiplicity 1. Okay, so these semantics are not quite comparable, and for that reason, the upcoming standards support all of the following. You can have unrestricted path, but if they contain a clean star that allows path of flexible length, then it must be limited by an upper bound on the traversal length. This would be the syntax there. Arbitrarily many repetitions of B, well, not quite arbitrarily, at least 1, at most 3. Okay, that would cut the infinite recursion. You can have a cyclic path. You can have simple, which they define as a cyclic, but you allow the source and target to coincide. You can have trails, and you can have shortest path, all of which are coming up. Okay, let's give you a flavor of the connection between the low-level computation model and the high-level query language, and how you compile from the latter to the former. And I'm going to illustrate that on the same shortest path example. I was mentioning before that it's a good semantics because you can count the number of shortest paths satisfying a pattern in polynomial time by not materializing the collection of all these paths. If you do, then you have the exponential blow up immediately. This is actually a sequential algorithm that has been known long ago. This is folklore. It resides on using a breadth-first search to the graph. However, it's the first time that we see it now implemented in parallel in a commercial system, exploiting the low-level paradigm that I introduced of edge map vertex reduced based on accumulators. Moreover, it is expressible in a high-level query language. So let's consider as an example this graph. Let's say that I start from the blue-colored source. Okay, that's going to be the initial frontier of my breadth-first search. And I'm going to initialize every node with the count of the path from my blue source, reaching that node at least so far. Okay, the blue node is reachable from itself by the empty path. And then I'm going to look at all the edges incident on my frontier. And in parallel, for every edge, I will write the count from the source node to the target node. Okay, at this point, you recognize that this can be implemented, specified as an edge map. Okay. And notice I have taken the one from the blue node, I have copied it to the two red nodes, which now become the new frontier, the new active set. And I repeat, from this frontier, I go through an edge map to the next frontier. Now the nodes in the new frontier each get a 1. And I repeat from them. And as I do that, an interesting issue arises. There are two incoming edges here into the same node. Each of them wants to write a 1 into its target. And I have to make sure here to not destroy the result through race conditions. I need the recipient to not miss any of the ones it receives. I need it to not depend on the order in which these ones are received. So this is a perfect application of an accumulator like the ones I've shown you. All right, and then one more step will take me to this frontier. And then a final step finds that node again, but another little thing to take care of is in the edge map function, the function checks first whether the target node already has a non-zero count, because if it does, it means it must have been reached in a previous edge map. So this current arrival at the node is not along the shortest path. So we're not going to write the 1 from the source of the edge into the target. We stay with 2. Okay, and at this point we're done. We have computed in this distributed fashion the number of paths for reaching every node from the blue one. And this information is distributed across the graph in these accumulators. Every vertex has that knowledge. And one last connection to high-level syntax, you can write what I just explained in this very short query, in which we have here source as a parameter of type vertex. We are declaring here a sum accumulator that takes integer value, call it count, which will be initialized at every node. The initialization is by 0 by default, so I don't have to specify anything new. I'm constructing an active vertex set, which initially contains just a singleton, the source I wanted to start from. And then I compute from this active vertex set, using this line here, a new active vertex set. And it's really the same, but what I do is, for all the nodes S in this vertex set, and there is only 1, I just add 1 to that accumulator. That's the initialization of the accumulator of my source. And then I enter this loop. So yeah, it's really important to have a bunch of control flow primitives to implement this kind of algorithms in a high-level query language. You won't get away without control flow. So while the active vertex set is non-empty, I'm going to just compute from the current active vertex set the new one. That's what the purpose of this block is. And notice what it does. It goes from vertex A in the active set, follows an edge of type E to a target vertex. It checks with this where clause that the count at that target in the accumulator at the target is 0. Remember, otherwise we're not going to write to it. Otherwise this node was reached in a previous iteration. We are not on the shortest path to it. Okay, but if this wasn't written to, then we're going to write now. And we're writing the value of the accumulator at A, the source of the edge, into the accumulator at target. And here, notice the plus equal says I'm going to add it into whatever there was there. I'm not going to just overwrite. And that's it. There are, of course, extensions to the algorithm. I've shown you only the shortest so that it can fit on a slide, but it's very easy to take this and extend it to start not from a single source, but from a set of sources, and also to count the shortest path that match a more complicated regular expression, not just E star. And all of this is expressible using the edge map, vertex reduce, accumulator paradigm, and therefore expressible in GSQL. Okay, a little bit more of flavor of what's to come in the standards. You've already seen examples of pattern syntax. Everything I've shown you was actually conformant to the 2 standards. Here, just to show you that you can complicate matters, I'm going from a customer C1 along a bought edge into a product P, and from a customer C2 along an edge of the same type into the same product P. And this, of course, is a typo. The incoming edge from C1 is, I bind variable B1 to it. for the incoming edge from customer C2, this should be a B2, sorry. Okay, so essentially you can write anything you could write in the conjunctive regular path queries of semi-structured data days, regular expressions, specifying really complicated chains of edge labels that have to be traversed. With clean start, disjunction, and so on. Plus, and this is new, the standard has also introduced the ability to bind a variable to the entire path traversed with the syntax you see here. So this is the same pattern as above, but I say P equals to introduce a variable P that will bind to the path matched by this pattern. Okay? And then the standard has a lot of syntax for what you can do to this path. You can iterate over it, sum up the weights in certain attributes to have the weight of the path, and so on. A lot of good stuff can be expressed. However, this is something that a bunch of us involved with the process try to caution against, because of course, this means that the user can now easily write a query that returns P in the select clause, and there are many P's. There are potentially exponentially many P's in the size of the graph, so you might have a huge result. Here a little bit more. How are these patterns then used? Well, they are parts of blocks, query blocks. And the block syntax will come in two flavors in recognition of the fact that there is a lot of adoption of graph querying languages coming out of the Cypher camp, but also in recognition of the fact that the programmers who are going to constitute the likeliest growth in adoption come from the SQL world. So here is basically the same query written in two flavors, where in the standard one of them is defined as syntactic sugar that can be compiled automatically to the other, but you can be compliant with the standard by writing either of these. So you can specify the graph in which you want to match this pattern. The match keyword says this. Then there's a where clause, like in SQL. You can further filter your matches. And then there is a return clause that, if you forget about the keyword and look at what follows, this looks like SQL. This would be the group key, and this would be the aggregate. You're counting all the customers, distinct customers, who bought a certain product whose name is Elmo. Okay, and you can even give a name to that column. So what this will output is actually a little table. And similarly with a select from where inspired syntax, very much in the same spirit. The interesting thing is that never mind how you specify one of these blocks, you can now chain them. By which I mean that you can look at all the variables that are in the return clause, either directly or given a name by the user, and you can invoke them as free variables in the next block. And that allows you basically to stack computation onto itself and take these intermediate results and build something from them, and so on. And this is known in the standard as linear composition. You perform a linear composition of the effects of these blocks. Another thing that is coming up in the standards, in particular in GQL, the first version, it will support two graph flavors, again in recognition of the two main communities from which it will draw its adopters. One of them is completely schemaless graphs. This is how Cypher was designed, and this is how we typically thought of graphs in semi-structured data days. However, in modern industrial adoption, it turns out that most customers want to know about the structure of the graph so that they can write meaningful queries. Also, they like the optimizations that come from knowing the structure. And therefore, there will also be an entire data definition language for specifying the graph schema. I haven't used the actual syntax. It's a little bit still in flow, but I have shown you the gist of it, the intention of it. I showed you a way to define that there is a product vertex type that has name and price, and there is a customer vertex type, and so on. Okay, so there will be syntax for that. In addition, there is in the Linked Data Benchmark Council a working group called LEX, which is extending the current design of GQL schema into much more sophisticated type system that supports open types. So I can say customers have a name and they have a credit rating, but they might have other attributes that I'm not bothering to list here, very much in the semi-structured vein, or closed types where you say, no, it's either one of the attributes listed here or you have a type error. And then you can organize these in subtyping hierarchies in object-oriented fashion. The vision being to support not just the two extremes, schema-less, schema-aware, that are currently coming out, but an entire spectrum in between. Okay, so in the interest of having time for discussions, I will close now, but I would like to leave you with a parting thought. To me, graph databases are more exciting than ever. Yes, we've seen them over 30 years, but currently, given the new computing infrastructures and the new industrial applications and scale requirements, this leads to green research pastures, and I'm looking forward to seeing where this research will take us. As we've already grown accustomed to, there is this debate that was never settled and is now raging more heatedly than ever. Do you do graph database storage and querying on relational backends or on native customized ones? However, here is another intriguing thing to consider. What about taking relational data and relational data analytic tasks, queries and such, and running them on a native graph backend? This may seem counterintuitive. It was usually the other way around. However, there is strong evidence, recent evidence, that this may not be such a bad idea. I had a PhD student, her name was Ainul Smagulova. She graduated in 2021, and she published a Sigmod paper then, in which she found a clever way to encode tables, so the rows in tables, as nodes and edges. One in which actually the values in the active domain appear as a certain type of node, and the tuples themselves appear as another kind of node, and you connect them by edges. If this value appears in that tuple, then you draw an edge between the vertex modeling the value and the vertex modeling the tuple. And then she came up with a clever translation from standard SQL into a language that allows you to speak high level about edge map, vertex reduce computation, and GSQL was her vehicle of choice, but it's really not about the syntax. It's about getting your hands without writing low-level C++ at all these aggregation primitives. And this way, she found a way to parallelize classical SQL computation. And she benchmarked this, and she measured significant progress with respect to the big ones, Postgres, SQL Server, even Oracle, on the benchmarks that they use when they play their own game, TPCH, TPC, DS. Her prototype did not beat Oracle when using column storage layout, but did not. But it was an honorable second place. And this was something built by a single student for a PhD thesis. And Oracle is very mature. So this suggests that there is something behind the edge map vertex reduce paradigm that gives it utility for parallelization of computations that transcends the graph setting. And personally, I find it very interesting to look into other applications. So with this, I would like to thank you for your attention and invite any questions.
Oh, okay, Alin, thank you very much. Very nice talk. It's expected. Well, I have many questions, but I will stick with one for the last work you've mentioned of your Sigmod paper. And when you say I'm going to use some native infrastructure for graphs, what is this thing you're talking about? Like when we talk about relational structure, most people know about it. But when you think about this native graph structure, what did you really use at that time?
Okay, so for this particular application, we used Tiger Graph, okay, which is not based on tables underneath. It has its own customized way to store the graph data, and essentially it's adjacency lists, okay, which means that if I have a vertex, I can immediately find the list of edges emanating from it just by reading it. So this ties back to what I was saying in the beginning. There is no need to join as you traverse. And yeah, in order to not have to start from scratch and build this using low-level C++ or such, she basically just used this, and she translated the SQL queries from the TPC benchmarks to GSQL queries, which are conceptually rather close. You've seen the syntax, so it's not such a huge step. Although, of course, the interesting part is the introduction of those accumulators and using them in smart ways. And there, what she did was to take ideas from worst-case optimal join algorithms. For example, if I want to find a cycle in the graph, and I traverse a chain, and then I have to find that the endpoints of this chain meet in some third node. So there is a bit of a triangle there, and there are cool ideas for triangle matching that come out of this worst case optimal join work. But these ideas are eminently translatable into writing the correct accumulators, reading the correct accumulators. That's what you did.
Hello, thank you so much for your talk, to come to Brazil to talk to us. It was a very interesting and exciting talk. And my question is, you have probably considered that, but since you didn't mention, I would like to ask you if you have tried to instead of putting it in a native store or relational store, putting it on a Spark store, Apache Spark, I mean. Because they have all this support for graph, both in GraphX and in graph frames. So my impression is many things that you showed here, for instance, in Tiger Graph, you could maybe implement on top of, for instance, graph frame, and you get the optimization for free if you do that. So have you considered that?
Definitely, that's a very good observation. Yeah, we have considered it. Let me first point out that if you look at GraphX, it is really only the programming abstraction that allows you to think like a vertex. The way it's built underneath, it's closer to the MapReduce primitive, and therefore there are some inefficiencies that already Google Spragle decided are not worth paying for, and that's why they went to a native graph, think like a vertex engine. But having said that, we have actually run GraphX in various benchmarks even prior to this paper, and we did not find it to be competitive. So we didn't include that here, and in particular in this case, Tiger Graph looked to be the winner.
How about graph frames? Have you tried that? Because with GraphX you don't have the optimization, so that's why probably it didn't work very well. But in graph frames you have the optimization. It looks like very much as relational optimizer. So
yeah, no, we have not tried it. In principle, one could, and if graph frames were to perform well, this would be another feather in Ainur's cap, because her whole point is, I'm going to put it on top.
yes,
Right.
I see that.
It's a good idea. By the way, she was hired by LinkedIn, who is building its own graph of LinkedIn accounts, and it's very possible that some of these ideas will be under the hood there.
Thanks so much.
Sure.
Thank you, Alin, again. Is it working? Nice talk. I recently, one of my students, he defended his thesis, and he was looking for, trying to answer the problem of see whether a certain link exists between two nodes. And he was looking in knowledge graphs. And well, the approach he took was to go towards machine learning and learning stuff. So one of the questions is, what's the space in this arena for machine learning models, and how do you expect those kind of new queries to arrive, and will be they syntactically answered as by following this path, or can they kind of learn the context from the graph and eventually answer at least existential queries? I don't know whether there are other kind of queries that it can help. Thank you.
Thank you. Yeah, this, first of all, the connection to the whole semantic web knowledge graph arena is obvious. And as a matter of fact, the two industrial camps are each trying to steal each other's lunch, and especially the generic graph database companies are now trying to support ontologies, knowledge graphs. I know that at Tiger Graph, they even started a project to support the standard query language Sparkle by translation into GSQL. And in principle, a knowledge graph is a graph. You can translate it to a property graph. There is some there are some challenges with all the automatic inference that happens when you add rules to your knowledge graph, which you don't have here. A secretary is a person. That looks like it would require a bit more research on how to reduce one application to the other. But in principle, one can bring this all together into a setting of graphs with constraints on them. And then how do you use this in how to exploit it in machine learning? At the very least, you want to be able to answer this kind of existential or point questions really quickly, because they will be posed by your learning engine. And this is something that I know a bunch of graph companies is working on now, and they're trying to sell their platform as the better substrate for learning. But of course, one can ask, can I go beyond? Can I do the learning inside the database? And that's exactly an entire direction that has been taken already outside of the graph world. And relational AI and its previous incarnation, Logic Blocks, was exactly marketing itself as doing just that, because all the machine learning algorithms ended up using some sort of iteration, some sort of recursion, which could be easily expressed in data log over the relations that model the graph. And then you could write a program that would do both the equivalent of SQL manipulations that pull some data out, and the program that learns iteratively, all of this in the same big data log program, hoping for optimization opportunities that reach across the boundary between SQL style manipulation and machine learning manipulations. So this already has been tried and is being hotly pursued in a non-graph setting. And of course, I'm sure that the graph industry will follow suit, and relational AI in particular is likely to do that first. Does this answer the question?
By looking at the graphs, you could try to learn and answer. So picking one of the points that you raised, I mean, the complexity of answering certain queries in large graphs, then if you are able to learn if a certain prediction can be true. So for instance, one typical example is to say whether Barack Obama is married with Michelle Obama from a graph. And without rules, still you can look at the neighborhood of Michelle and neighborhood of Barack and have a certain probability that they are married. And these are, I mean, they can look only in the graphs without rules and so on, and still at least approximate an answer. So
right,
I was looking for this, build that be a tool for very large problems to be solved, like in indexing, learning indexing stuff and so on.
Right, definitely. So the kind of computation that underlies this kind of questions can be expressed using this kind of aggregation primitives that I have talked about. And in principle, what you have learned can also be incorporated back into the graph. There are, at this point, I'm aware in the industry of efforts to define what is known as virtual edges, that are the result of a computation. Then you put the edge in there, and from now on you can write programs that just cross it without having to do that computation. This is really an instance of materializing computation. And I can see how whenever you enrich your graph with knowledge, you may want to add this kind of information. And that the graph storage of tomorrow will definitely support it. They are much more ambitious than that. They don't want to be the platform under the machine learning application. They want to pull the machine learning into the graph engine itself. They come with various libraries nowadays that do various tasks, graph theoretic tasks that are relevant to machine learning. And in the case of query languages like the one I've shown you, you can actually express these algorithms in the query language. You don't have to go all the way to low level, which means that the user can open the library, sees a few lines like I've shown you, and that's community detection or recommender systems and so on. And then they can just edit it themselves and adjust it as they need for their particular case. So yeah, there will be a tight coupling between the communities.
And I think we are, do we have time, I think? Any more questions? No? Thank you, Alin, so much for a very nice talk. I think he'll be available until tomorrow, right? And so please catch up with him during the coffee breaks to ask more questions or other.
Friday as well, unless you're kicking me out.
Fridays as well. Okay, good. More time.
Thank you all for
thank
coming.
you so much.
Um minutinho só, peço para vocês aguardarem aqui. So we thank you once again for coming, for accepting our invitation. So we have a small gift for you from Belo Horizonte. So Sérgio, please.